Okay. So it's up to your choice. You make this in series in parallel. Okay. So let's, we plan to do in parallel. Okay. So I just zoom out and align this on the bottom side of the screen so that I can place the PMOS on the top side. Then again, I click MOSinator. This time I select a PMOS. Now when I check the update the current values, the values are around 2 milliampere. So that's okay, because you remember the PMOS has lower mobility and hence lower current. So to match up the current, it is, I just make this as 1.5, 1.67, yeah, around 1.7 micrometer. Okay, for 1.7 micron, it will give me almost of the same amount of current which NMOS was producing. So I say generate device and you align it and place on top of the NMOS. Okay, so I zoom this area. Yeah, so you can see that they are a little bit not that well aligned. It was a little bit offset. So I can just click stretch and move, select the NMOS and shift it towards a little bit of right. Yeah, so now it's better. Then I select the tin gate and short the gates of all transistors. Okay. And one horizontal line also. So this will short all the gates. So all transistors are in connected, because for inverter P and N both have the same common gate. And plus they are all in parallel. So all gates are shorted. And on any one of the side you can short it, bottom, top, or the middle side. Okay, then I take the metal line and I short the bottom side of the PMOS and the top side of the NMOS metal terminals which were, coming out. So that's it. And also short the bottom side of the NMOS. So the NMOS become in parallel. Then I go on the top of the PMOS so that I can short the terminals which are extruding from the top side. Okay, so that will make the PMOS in parallel. Now I have to just bias them. So I take a VDD supply for the metal one, VDD supply for the anvil, just drop it on the anvil, don't drop anywhere else. Then I take the ground and connect with the NMOS terminal. Then I take a square clock, apply it to the gate, make it 1 nanosecond and 1 nanosecond. And this is the node I want to observe, S1, let's say, no problem. And a capacitor of 0.5 picofarad, I think, or 0.05, 0.5. Yeah, okay. Then I just change the color and I just change the time scale. So here we can see that this is oscillating. I just check the frequency. So the frequency is 500 megahertz. Okay. So this guy can operate at 500 megahertz within rise and fall time of almost less than 80 picoseconds. So I designed something better than what I wrote. Okay, so it's all about the reverse calculations. The current what I anticipated was 3.5 milliampere was a little higher than my expectations. So I should have done maybe 2.5 milliampere. Then that would have been better. And this is all simple maths, like this is RC time delay. So it's like the charge time constant is 0.7 RC, something you can set up this value, okay? So this is it. I believe everyone is clear on till this end. Any questions till now? I just pause for a moment, maybe 10 seconds, and ask if someone was not clear what I just did now. Okay, so everyone is good till this now. We are on the same page. Okay, great. So let's move ahead. Okay, so I just go back to simulation. So what you are seeing in this simulation window, we understood this from past 2-3 days. We are looking at this simulation run. So this gives you voltage versus time plot. So on the tops, I mean, the y-axis you have the voltage, and on the x-axis the time reference. So how, with respect to time, this design is progressing. So that's we are looking at. Now, if you go to voltage versus voltage curve, so this is another plot. So this plot tells you about, on the x-axis there's your input voltage, and on the y-axis is your output voltage. And this is called a DC transfer curve, or voltage versus voltage plot, or I think gain plot bhi kehte hain kuch log usko. So it has many synonyms. Maybe I'm not familiar with all the synonyms, but this is a good enough to see. I think everyone must have seen this plot in their books or in the classrooms, anywhere. You can tell me that no sir, ye kuch naya hai, something which we have not seen, so that maybe everyone is familiar. Anyone, you can, I'm sure that there would be more number of yes as compared to no's. Anyone with a no, that you can write. Don't need to write, no need to write yes, because I know, I'm pretty damn sure that most of you must have seen it. Okay, so this is called as transfer curve. Okay, so this is input versus output plot. That, okay, how much voltage you change at the input, then how much output you get. Okay, and okay, so if this is clear to you, then you see there is a crossover voltage flag on the right hand side of the simulation window. If you click and click reset, so what does it say? It says that the VC is equal to 0.582. Okay, so that means this guy says that, boss, ideally the I just take a print screen first. Just a second. I just share something and then we talk more on it. Okay, so you see that this guy tells me that this is the quiescent, this is the crossover voltage, or simply called as quiescent point. Okay, so this is the point at which both the transistors have an equal drive strength. Okay, दोनों transistors की drive strength same होती है. वैसे इसके काफी सारे एक्सप्लेनेशन, sorry, I'm sorry, I forgot, Hindi is restricted. Okay, so at this point, actually, both the transistors have equal drive strength. But that means that both will have almost the same amount of current like produced. Okay, current output. Or actually, it is also an indication that this is the point at which both the transistors they change over their mode of operation. Because if you know that at this point, okay, at this point, what is true, that the PMOS is on and NMOS is off, because the input is less than the threshold voltage. You see this? The threshold voltage is 0.4 volt. You remember that the day one or second we saw this 0.47, 0.4 is the threshold voltage. Okay, so the input is less than the threshold voltage. You see, at this zone, the input is less than the threshold voltage. So the PMOS is on, it's fully saturated, and NMOS is off. Okay. Now what happens after the 0.8? You know, above the voltage of 0.8, what happens? The PMOS is turned off and NMOS is full on, or you can say it's saturated. So that means this guy, I mean, NMOS is pulling down the output to the low level. That's why you see that it is less than the 0.1 volt or something lower than that. Okay, so output is pulled down to low. Okay, but what happens in between? Okay, in between this zone, okay, over here. So over here, when input is around 0.6, okay, so both of the transistors, they are almost at the same drive strength. Okay, and hence they are, you know, swapping their mode of operation. So ideally, this quiescent point should be the half of the supply. If you're working at 1.2 volt, then it should have been 0.6 for a switching best switching characteristics. And if you're working, let's say, at 5 volt, it should have been 2.5 volt. Okay, it should be on the center of the noise margin areas. Okay, And as of now, we are working at 1.2 volt. So ideally it should have been 0.6, but it is coming at 0.582. So that means it is slightly towards the NMOS side. It is a little bit, it's a kind of tug of war, and the NMOS is a little bit more stronger. So hence, NMOS is pulling down the quiescent point towards the lower side. Okay. So what makes the quiescent point? So as we said, the quiescent point is the point at which both the transistors have equal drive strength. Okay, or it's just like that. Who has more current will pull the quiescent point towards itself. Okay, it'll pull the quiescent point itself. So if the PMOS has more current, the quiescent point will be towards the positive side. If the NMOS has more current, it will be towards the lower side. So let's validate this. Okay, and come back on microwind and see that does it make it or not. Okay, I think that's this one. I just close my other windows. Okay, so this is the voltage versus voltage curve. So what I do, I just save this file. Okay. Okay. And you remember that the quiescent point, what did I ask? Close to 0.25. Okay, I want something closer to 0.25. So it should be pulled down towards the lower side, right? It should be pulled down to 0.25. Okay, so what I do, I just remove the NMOS side. Okay, I just remove the part of the NMOS and these things. Okay, I just delete the NMOS transistor. Okay, and I remake the NMOS transistor. Okay, and as you remember, the PMOS was having a drive strength of 3.5 milliampere. Okay, so I go with it, and I make NMOS something more powerful. Okay, maybe 5 milliampere, 5 micrometer. So I made an NMOS that wide, which is around having 17 milliampere of current, and I just place the PMOS on top of it so that we can just simply connect easily and redo the simulation. Yeah. Uh-oh. Okay, so I just join them. So I take the gate material and short the gate part. Okay, I take the metal one and I short the nodes which are extruding from the NMOS and PMOS side. I take a capacitive load of the same value, 0.5 picofarad. I take the clock and apply it to the gate, and the same clock, but the name is clock 2 this time. And I just go to the bottom of the NMOS to short the metal lengths. It's quite long transistor. Yeah. And I short the metal nodes which are extruding from the bottom side, and I just connect and ground to this guy, VSS. Okay, and it should be ready to simulate. I just change the color and simulate this again. Okay, I forgot to add the output node. Okay, I just zoom this area. I just take the visible node and call it S2. Okay, and simulate this guy. So here you can see that the rise time performance is the same, 78 picosecond, but the fall time performance has improved drastically. It's 16 picoseconds now, but then it's correct because we have given enormous amount of current to the NMOS. NMOS is around 17 milliampere of current. Okay. Now, if you go to voltage versus voltage curve, what do we see here? So instead of 0.58, it is coming 0.35. Okay, so definitely we have made an improvement. We have shifted the quiescent point towards the lower side. Okay, but probably looks like my current calculation was not enough, and probably my current should have been more for the NMOS so that it can produce or it can drift the quiescent point towards the lower side. Maybe I can just give one more attempt. I just save as this file and call this as second file. And for the quick demonstration, either I can now, there are two methods. Now either I can either increase the current of the NMOS, or maybe I can just decrease of the PMOS. It's one and the same thing, okay? Anyone doubting on that कि नहीं sir दोनों एक बातें नहीं होती, आपको NMOS को ही बढ़ाना पड़ेगा. I mean, you have to increase NMOS only, not PMOS. You can always doubt. So making the PMOS again is like I can just delete some part of the PMOS. I just take the delete button and just click delete. That's it. Okay, and I just take this shift and move and bring it down. Okay, and make corrections like stretch and move. I take the end well, I stretch it, and I take the tin gate and I can zoom in between so that you can see nicely what I'm doing. So I take the tin gate, I short these gates. Yep, so they become parallel again. So what I've done, I've just deleted this part. I'm sure I would be violating some DRC, but I'm not bothered about the rules as of now. So I have made the PMOS a little smaller as compared to the previous time. Okay, just a second. I forgot to add the metal lines. I have to join the metal lines also, alternate ones. So it's still working. So you can see there is an impact on the rise time. Instead of 78 picosecond, the rise time has climbed to 130 picoseconds. That's true because I made the PMOS smaller. The width is smaller now. So if lesser the width, lesser is the current. Lesser is the current, more is the rise time. Simple. And if you go to voltage curve, so you can see that it has came a little lower than the previous one, 0.316. So definitely we can pull it down to 0.25, but it looks like you have to push more amount of current to it. Okay, so this is how you can control the quiescent point biasing. I mean, who is winning the tug of war, NMOS or the PMOS? Okay, so more the powerful the guy, more powerful the tug would be. Okay. So this was the experiment all about, just to see that how you can control the quiescent point. That's it. Okay. Any questions to it? If you have any questions, I can just wait for a few seconds. Then we can start our routine work. I can ask you to make something more interesting design and follow through it. No doubts, no questions. Shall I proceed? Okay. Any specific doubt? You can ask over the voice chat, so that's more faster. No doubts. Okay, fine. No doubts. Okay. I thought, no, I should not proceed and continue with the explanation. Anyhow, so this was an interesting design to see that, okay, how to play with inverter and what stuff you can make with inverter. Okay, so today in the first half, we will see a little bit more of inverter and we will make something better of inverter. there are two things I wish to ask you to make. One is an amplifier with an inverter, okay, and you have to make a ring oscillator with an inverter, okay. So let's proceed. Meghna, you have any, I mean, no what, like no doubts, or don't proceed? No. So I just reopen my design, which I just made now, and the first inverter what we made. Yes, if you have any doubts, please ask over the voice. Okay. Okay. Great. That's good. I'm happy to see there are no doubts. Okay. So we come back to the same inverter what we just made now. This is a multi-finger inverter, and having a specific load and everything is all right. Okay. And we try to make an amplifier out of it. Okay. So what can we add or delete to it to make this inverter as an amplifier? Any questions over here? I mean, sorry, I don't need questions. I need answers actually, or comments. That if I have to make this inverter as an amplifier, what shall I do? I mean, shall I cut something? Shall I add something? Do nothing? Or maybe add an inductor, or maybe add an amplifier to it? What? What are your inputs? How I can use inverter as an amplifier? I just hold on for a few seconds. You can turn on your microphones and speak. Okay, that's good. You can speak, dear. That's much more better and faster, and will save a lot of time in typing. You can just unmute yourself and just talk to me directly. Has anyone seen earlier making inverter as an amplifier? Has anyone done this earlier, or maybe heard of this earlier? First of all, let me ask this question. That's a simple yes or no answer. Okay. There are a couple of no's. That's okay, no problem. Okay. So let's start with what is an amplifier? Anyone who can amplify a signal is an amplifier. That's an engineering answer, okay? But okay. So amplifier is a person who amplifies signal, okay? So let's see how does an amplifier works. Okay, so you just remember this inverter. I will not make any architectural changes in this. Remember, I'm not making any architectural changes in this inverter. Okay, so what is required is you go to simulation window first, and voltage versus time is not important as of now. Okay, feedback, adding a feedback is also not required because we will make an open-end amplifier. Okay, feedback is for corrective purpose. We are not doing a corrective versions, okay, as of now. Okay, it's just a simple amplifier. Okay, simplest of all. So you remember this plot. This is a voltage versus voltage plot, or the transfer curve plot. This is also called as transfer curve. Okay, so transfer curve is what? A plot between the output versus input. Okay, So what do we do here is, I just taken a screenshot of this. You are able to see this one, right? The sketch. Okay, so I believe you are able to see this sketch, right? Of the transfer curve. I just took a print screen. That's it, nothing more. Okay, so this is called as transfer curve. Okay, this is about transfer curve. Okay, my pen is not working. Yeah, yeah. So this is also called as transfer curve. Okay, so that is, the gain is generally is called as like this. Okay, so it is ideally, it should be like this. Okay, this is an ideal curve. Okay, where it should have a 90-degree turn of the output versus input, but that do not happens in the practical life, and we get something like this. This is what we are getting at. Okay, so what happens in these stages? Okay, so at this stage, what happens? The PMOS is on and NMOS is off. Then after this, what happens? NMOS is on and P is off. I believe everyone is clear about this. Any doubts over here? If you have any doubts, you can ask. Yes, make them operate in linear region. That's right. So this is it. So this area which is there, this is the place at which both of the transistors are in linear region. Okay, they are in linear mode of operations. So that means with respect to input, their output current is in linear range. That is important to understand. Their current, okay, their output current is a linear equation with the input voltage. So as you are increasing the input voltage, okay, the current of the PMOS is decreasing, okay, and the NMOS is increasing, and hence that's why the output voltage plot is also a linear factor. Okay, so this is how it is, and I just clear this. So that means this is having something like this plot. Okay, so this range is what? Okay, so this is the V in, okay, and this is what? This is your V out. Okay, so that means if any voltage you give, any signal you give, you will get something like this, isn't it? Okay, so that's why you get such kind of plots, which is if I draw like this. So here your input voltage is very short. If you give a signal over here, you will get output voltage like this. Okay, that will be more amplified. Okay, so if we come back to the sharing, okay, I believe you are able to see the share of microwind. Okay, so if you see this quiescent point, so that is a quiescent point. Okay, so at 0.582, both of the transistors are in the middle of the linear region, and anything above and below of this point, both may go into saturation regions. Okay, so this is around 0.6. Ideally, it should be half of the supply. Now, if you look at the slope of it, of this gain, I mean this linear region, okay, so the slope is -5 almost. Okay, so that is the gain you will get. And as this is an inverter, so this is what the gain you are getting, it's -5. Okay, so if what I do, I just apply a signal to the input. Okay, I just zoom in the middle area of the inverter and I double click on the clock. I double click on the clock. You must be seeing this clock window. So I just go to sinusoidal waveform, which is written as sinus. Okay. I give him an amplitude of 0.01 and frequency maybe 500 hertz, 500 megahertz, and offset of 0.82 because that is the same fusion point I got in the simulation. Okay. And I just say assign. And now when I simulate this design, so what do you see over here is you see a very small sinusoidal waveform is being amplified to a bigger one. Maybe I should increase the input voltage so that I can see a drastic change in the output. So I'll make it 0.05. So multiply by 5, so it should be 0.2, not enough maybe again. Yeah, that's still good enough. So you can see that this guy is working as an amplifier. Okay, so you give a small amplifier waveform and it produces a large varying sinusoidal waveform. Okay, so this inverter is working as an amplifier. Simple as that. You can make use of this amplifier to do anything you like. Okay. So any doubts or questions you have, you can ask me on this. Any questions you have? No? Y offset was 0.582 because both have almost the same drive strength. Both have almost the same equal current drive, PMOS and NMOS. So it's like, a tug of war. It's a tug of war. NMOS is trying to pull down and this guy PMOS is trying to pull up. So both will have a straight line a same steep slope if both have the same equal drive strength. Anyone having more drive strength will pull the Q point towards itself. Why there's a 90-degree phase shift at the output? You mean in this amplifiers? Okay, so because that's an inverter. You give him you give him logic high, it'll always give you logic low. Okay. And 180-degree phase shift almost. Okay. Because this is an inverter, that's why a phase shift. That's why he gives an inverting output. And this is just a basic amplifier. Technically you can't make use of inverter as an amplifier in any of your projects. Okay, because the gain and the current will keep on changing with the slightest change in the load, which is not required, which is not desired in a professional amplifier. Voila.
So what do you have added to make inverter as amplifiers?
What to have an inverter as an amplifier?
What you did in this?
I did nothing. I just changed the input. I did nothing. It is already an amplifier. And this guy has a transfer function. Anyone with a transfer function can work as an amplifier. Okay. The amplifier's gain should be there. Either anything above 1 or anything below 1. Then it can work as an amplifier. Why square wave is not amplified? Okay, that's a good question. Very good question, in fact. Because we are not working in a linear region with the square wave. The square wave we applied that do not work in the linear region. Okay. You look at this. It either works on the saturation of the PMOS and NMOS. Okay. Because NMOS is on, okay, or the vice versa, that PMOS is off and NMOS is completely saturated, okay. So it do not works anything in between. And in fact, actually, technically, it works in amplifier because anything lower voltage will also would be restored, because if you go back to the signals of the clock, you see this, that the level 1 voltage is 1 volt, but I give him 0.9, and level 0 is not 0, it's I just give him 0.15, something a noisy kind of. Okay, it's not noisy, but like the levels are shifted. But what do you see? You see here, this is also amplified now. But here still I'm not working in the linear region of this, because if you want to have analog kind of amplifier, because that's what we are habitual of seeing from the eyes, that we need to see a sine wave as an amplified signal. Okay, so that's why we work on the linear range, because if you apply a sine wave over here, it will be converted to a square. Any other question? Okay, then let me ask a couple of questions. Okay, I'll give you a few seconds to solve those questions. First of all, let me pop up the problem. Okay, and I apply the same inverter. I'm not touching the inverter architecture. Okay, I'm not touching the inverter architecture, nothing at all. It's just a simple clock with 1 nanosecond low, 1 nanosecond high, and the levels, if you want, I can shift, or I can make back to a strong input also, so that you don't get confused on that side, because it has no relations to that. How much power consumption do you see? 0.25 milliwatt. I just go more, and it is CU 500 giga, I mean 0.5 gigahertz or 500 megahertz signal. Okay, the inversion is this. So you see almost the power consumption is constant, which is 0.25 milliwatt. Is this okay? First thing you establish is that the power consumption in this simulation run, what you see is 0.25 milliwatt. Okay, you remember this. Now I just go to the signals. Instead of clock, I apply sinusoidal signal, and the frequency is the same, 500 megahertz. And the offset is 0.582, right? The same offset, and amplitude I give this to 0.5, 0.25, I think 0.5. And let me check it is coming above or below. No, it's going above. Okay. Okay. Anyhow, so I think this will also work. It should be having 0.6 or 0.582. Okay, 0.5. So I give a sine wave, which is a fully blown sine wave. Okay, it's just like fully grown sine wave. So what it does, it just works as a square wave converter. Like any input sine wave, he'll convert into a squarish waveform, because he's working at the quiescent point above. Okay, so, or in fact, okay, let's come back to the same amplifier logic first. I give a 0.1 amplitude sinusoidal waveform, which is a very small sinusoidal waveform. So you can see that it amplifies a signal. Okay, he amplifies a signal. Okay, maybe not exactly of the same shape of the sine wave, but quite close and good enough. How much is the power consumption? How much is the power consumption? It's 0.892. Almost 4 times. Almost 4 times. Okay. So obviously you are looking forward for a known question, that why the power consumption shooted up. Because you remember power is proportional to FCV square, right? Power is proportional to frequency into capacitance into voltage square. Did I change voltage? Did I change frequency? No. Did I change capacitance? No. Did I change the structure or the architecture of the circuit? No. Then why my power consumption is coming so high? I answer this, don't worry. Why square wave was not amplified? Any answers? Why do you see that the power consumption of the design has gone up to 0.9 milliwatt, almost 0.9? Voltage, what voltage? Which voltage we changed? गेन, ड्यू टू गेन की वजह से हमारा सब बढ़ गया. हाँ, मतलब ये तो वो वाली बात हो गई कि जितना मुनाफा ज्यादा उतनी मेहनत ज्यादा. That's relatively true. That's true. Anyone else? Oh. Okay. Well, because both of the transistors are working in a linear mode of the operation. They never get saturated. Okay, they are always fully on. They are always on. Because what happens in this voltage versus voltage curve, if you see this, so what happens that I just take the print screen. Okay. I just take this snapshot and show and explain. So as you see this one, and over here, what happens that the PMOS is on and MOS is off. So that means at least one of the guys totally turned off. So your power isn't under control. Reverse happens over here. NMOS is on, PMOS is off. So at least one guy is off. But during this range of operation, both guys are fully on almost. They're almost fully on. Okay. So what is happening? This is a kind of short circuit power dissipation, because this guy is draining current and this guy, is this guy sourcing current and this guy is draining current. So they are playing the tug of war. And you remember when the tug of war you play, you consume huge amount of energy. So this is what is happening. The current is rushing from power supply to the ground. Huge amount of current is being rushed. So hence this guy will consume such amplifiers will consume huge amount of power if you want to make them operate. Although technically all the amplifiers consume huge amount of power, all the amplifiers, but they can be controlled with a better architecture instead of this architecture. This architecture is very poor in power consumption control for amplification purpose at least. And square wave gets, if you give a sinusoidal waveform with higher voltages, obviously it will look like a squarish. If I give him something like 0.2 volt and so you see that this is something like 0.2 volt above and 0.2 volt below the quiescent point. And I think I can.
So we are not visible.
Oh, sorry. I forgot to share back when I came back over here. Yeah. So I just gave him a square wave with, sine wave with a higher magnitude. So it will keep on squaring the signal. It will keep on squaring the signal. Only the sine wave which was in the linear region, that would follow through. Okay. So maybe I just increase the voltage more. So this is a sine wave with a full scale plus minus voltage from the quiescent point. So as you can see, that it will almost convert into a squarish waveform. Okay, because after the quiescent point, things will flip over. Okay, So this was about like quiescent point, power consumption control. In this case also you can see the power is higher, but still considerably lower than the amplifier case. Okay. So this was about inverter segment. Now let's take something on maybe ring oscillator. Yeah. Okay, we will design something ring oscillator and the gates will, what did I say? One more thing. I think ring oscillator. Okay, I will remember. Oh, it's 4:30. So how long you guys want break? 1 minute, 1.5 minutes? Or yeah, I stopped the screen sharing. So I'm just confirming that how long you want break. 3.5 minutes. That's a good calculation. Okay, no problem. 3.5 minutes. So we take a 5 minutes break. No problem. Okay. So we come back at what, 16:40. Okay. In my clock it is 16:34 and a half. So in 4-5 minutes we join back again. Okay. Let the your systems be as it is, so we don't lose the connection. See you guys.